As we continue with the mathematics of artificial intelligence, we now look at the tiny math rule that trains giant AI models. Okay. And of course, the tiny math rule is basically chain rule, right? And in addition to that, we'll be looking at things like gradient flow and back propagation. So the chain rule is one of the most important ideas in calculus. Although it is only a single differentiation rule, it is the mathematical foundation of modern deep learning. So every time a neural network learns from data, it computes millions or even billions of derivatives. And these derivatives tell the model how each parameter should change to reduce prediction errors. So the algorithm that performs this computation is called backpropagation. So, putting backpropagation together with chain rule, we have this a serious thing about neural networks. So, and it is nothing more than repeated application of the chain rule. So backpropagation is simply the repeated application of the chain rule. So in this lesson, we will study composite functions, the chain rule, work to differentiation examples, computational graphs, gradient flow, backpropagation, why giant AI models depend on this tiny calculus rule. And the objectives are as follows. After completing this lesson, you should be able to explain what a composite function is, state and derive the chain rule, differentiate nested functions, understand gradients and gradient flow, explain how backpropagation works, apply the chain rule to neural networks, and of course, understand vanishing and exploding gradients. Now, one of my earliest playlists on this channel is basic calculus. So if you go through that, you will see the length and breadth of calculus. And part of that is the idea of chain rule and other things. The idea of chain rule, composite functions, and everything like that. So in case you need a proper foundation in that regard, you want to check out the basic calculus playlist on this channel. So let's go ahead and talk about why why AI needs calculus. So why does AI need calculus? Suppose a neural network predicts cat to be 10%, dog is 85%, and horse is 5%. If the correct answer is actually dog with that 85%, the prediction is good, of course. If instead the network predicts cat to be 90%, dog is 5%, and horse is 5%, the model has made a large error because dog is actually the correct answer. So to improve itself, the network must answer an important question. Which weights caused the error, and by how much should they change? So if the 90% attached to the cat caused the error because it is misleading us, the answer is dog, whereas it has 90% for cat. So it is not only saying cat is the right answer, but it is even saying that with 90% level of confidence. So you see that has to change. So which weight caused the error and by how much should they change? So to answer this question, we compute derivatives of the loss function with respect to every parameter. Mathematically, we compute the L, the W, where L is the loss function, W is the trainable parameter, and the chain rule allows us to compute these derivatives efficiently. Now, we move on to talk about composite functions, which is a basic mathematical idea. So the chain rule applies whenever one function is placed inside another. Suppose that, G is a function of X, and then F is in turn a function of G. So it's like F is a function of G, and G is a function of X. That is chain rule, basically. It's more like function of a function. So here, G of X is the inner function, while F is the outer function. So the output of the inner function becomes the input of the outer function. So whatever output g of x gives, you throw that into f, and then you get the result. For example, g of x is 3x plus 2, whereas f of u is u squared. So then you can say that f of g of x is simply, so now g of x now takes the place of u. So if g of x is 3x plus 2 and f of u is u squared, then f of g of x would mean you now have g of x taking the place of u. And since g of x is 3x plus 2, so instead of u squared, we then have 3x plus 2 all squared. And this is called a composite function, like that. And then talking about the chain rule itself, the chain rule states that the the derivative of f of x of g of x is actually the derivative of f prime of g of x. F prime is the derivative, right? So that's f prime of g of x multiplied by g prime of x. Now the rule can be remembered as this: differentiate the outer function, then leave the inner function unchanged, multiply by the derivative of the inner function, right? So we have this kind of thing here. So, so a common memory aid is this. You have outside multiplied by inside. So why the chain rule then works? Suppose that suppose u is g of x and y is f of u. So since u depends on x, so you see here, u depends on x and y depends on u. So it means y is a function of u, whereas u is a function of x. So it means y is a function of g of x. So since u depends on x and x change and a change in x rather changes u, and that change propagates to y. So therefore, dy dx. So u depends on x and y depends on u. So that means that dy dx will be the change in u with respect to the change in y with respect to u multiplied by the change in u with respect to x, such that it technically looks like the u can cancel the u, so you have dy dx at the end of the day. This equation is exactly what you call the chain rule, and that can happen for more functions, which is the reality with artificial intelligence. So it tells us that the total rate of change is the product of the local rates of change. So the rate of change here of y with respect to u multiplied by rate of change of u with respect to x gives us the overall change in y with respect to x. So look at this example. So you want to differentiate y equals 3x plus 2 squared, like we saw before. So of course, the outer function is u squared. So this is u squared right here. So the derivative is then 2u. Okay? The derivative is 2u. So if you replace u with the inner expression, which is 3x plus 2, you then have 2 times u, which is 2 times 3x plus 2. So if you then differentiate the inner function, that's 3x plus 2. So the derivative is 3. So the next step is to then have dy dx, which is 2 into 3x plus 2 multiplied by 3. And all of that will be 18x plus 12. Well, to make it more systematic, right? You have y equals 3x plus 2 squared. Y y equals 3x plus 2 squared. So here you can say let u be 3x plus 2. We have that in place. So if u is 3x plus 2, that simply implies that y now is equal to u squared. So that's one way to look at it. So then you can say, so du dx here, du dx, that means differentiate 3x plus 2, you get 3 easily. And then for this, dy du, differentiate y with respect to u, that's 2u. Okay. At the end of the day, we know that u here is 3x plus 2. So since u is 3x plus 2, we can then say that dy du is equal to 2 into 3x plus 2. If you like, you can open that up, but we can also leave that. Then overall, you can say, so overall, dy dx now, dy dx is now dy du multiplied by du dx. So dy du is 2 into 3x plus 2. So dy dx is equal to 2 into 3x plus 2, which dy du is, multiplied by du dx, which is this 3 here, so that dy dx now is equal to 6 into 3x plus 2. And finally, dy dx is equal to 18x. Dy dx is equal to 18x plus 12. And that is what we have that way. So that's the systematic way to go about it. Now, of course, we can use SymPy to take care of that too. For the Python verification, import SymPy as SP. So x is equal to SP dot symbols. So the symbol of is x. So y then is equal to 3x plus 2 all squared. And then if you differentiate that, you take the differentiation function from SymPy, you differentiate y with respect to x. So you have 18x plus 2. And that's the result right there. So example 2 now, you have y equals sine x all squared. So the outer function is actually sine u, meaning that x squared is u. Then if you differentiate sine u, you get cos u. So replacing the inner function gives cos x squared because u is x squared, right? So now differentiate the inner function. So you have d dx of x squared, that's 2x. Finally, dy dx is 2x cos x all squared. And that's the result you get. Of course, if that looks somehow to you, let me go back and do what I did before. So we have y to be sine x all squared. Y is equal to sine x all squared. So you have y is sine x all squared, sine x squared rather. So you can say so you come back and say let u, or it doesn't have to be, it can be anything. Let u be x squared. So that implies that y is equal to sine u. Okay, so you then differentiate each one. So du dx is equal to 2x, and dy du is equal to cos u. When you differentiate cos, you get sine. So dy du is cos u. And then, of course, you know u is already x squared. So based on this idea, it means that dy dx is equal to cos x squared, like that. So overall now, you have dy dx, which is equal to this is dy du here. This is dy du, not dy dx. So dy dx is now dy du multiplied by du dx. So that dy dx now is equal to dy du. So dy du is 2x, and du dx, sorry, dy du is cos x squared. This is cos x squared. And du dx is 2x here. That's 2x. So that dy dx is equal to 2x cos x squared, and that is what you get. So that's a more systematic way to go about it. So of course you can have so you have 2x cos x squared. So again, you can use SymPy. So the symbol is x. So differentiate uh y is sine x squared. So differentiate y with respect to x, and you get 2x cos x squared, like that. Example 3. So for example 3, differentiate y equals e raised by 5x cubed. The derivative of the outward function will be, so imagine 5x cubed is a function on its own. So if you differentiate e raised by u, you get e raised by u, same thing remains. Then the derivative of the inner function is, then if you differentiate 5x cubed, you get 15x squared. So if you put everything together, the y dx will be 15x squared e raised by 5x cubed. Well, that may look somehow, but let's go ahead and do the same thing I've been doing with the rest. So y equals e raised by 5x cubed. Y equals e raised by 5x cubed. So you have y equals e raised by 5x cubed. So to do this, we can say let u be 5x cubed, and that implies that y is equal to e raised by u. Okay, so here du dx now is equal to, differentiate this now, you have 15x squared, and here dy du, when you differentiate e raised by u, you still get e raised by u, but now u is 5x cubed, so that means that dy du is equal to e raised by 5x cubed. So put everything together. So dy dx is equal to dy du multiplied by du dx. Dy du is e raised by 5x cubed. Du dx is 15x squared. Everything together is 15x squared e raised by 5x cubed. And that's the result right there. Okay, so we have that example 3 there. Of course, we can do that using SymPy also. So same procedure. Y is exponent of 5x cubed. So differentiate to get 15x squared e raised by 5x cubed, like what we got over here. 15x squared e raised by 5x cubed. Now, let's talk about multiple layers of composition. Now, so we've been having inner and outer function, but here you can have multiple, you can have a function in a function in a function in a function, and it keeps going like that. So we can have multiple layers like that. So multiple layers of composition. Consider y equals sine e raised power x squared. So you see, x squared can be u, and then you now have sine e raised power u. And then y, so v can then be e raised power u. So you now have sine v. There you have 3 layers. So this expression contains 3 nested functions. Starting from the outside, you have sine u. Okay. And when you differentiate sine u, you simply get cos u. And that gives you cos e raised power x squared, because u is e raised power x squared there. Then next, e raised power x squared is another level. So if you differentiate e raised power x squared, um, if you differentiate e raised power x squared, you get that. Finally, x squared is then 2x, and then you put everything together. Notice that every additional layer contributes another multiplication. Okay, so to make it clearer, like I've been doing, so y equals sine e raised power x squared. Let's do that. Y equals sine e raised power x squared. So y is sine e raised power x squared. So what are we doing here? So we say u be let u be x squared. So this x squared here. So if u is x squared, that implies that y is equal to sine e raised power u, like this. So again, another level to this, you now say let 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 v let v now be e raised power u. Okay, this e raised power u. So that implies that y is equal to sine v. Okay, so be careful with v and u, they are different. So now we have three layers. So what do we do? So we have three layers. We have e is x squared. We have v is e raised power u, and we have y equals sine v. So what do we do with that? So for this now, we know that du dx is equal to 2x settled. Then for this, we have that dv du. When you differentiate v, for v with respect to u, you get simply e raised power u. Nothing changes. And then coming here, you have dy dv. Dy dv, when you differentiate sine v, you get cos v. So what you have to do next is to replace what you have to replace. So we know v is u, right? So we know this is sine v, this is cos v. So we know v is e raised power u. So what do we do? So based on this idea now that v is e raised power u, we have dy dv to be equal to cos. That v is e raised power u. We have that. And what else do we have to do? So this one now, let's bring it down. We know that e raised power u. So we know that u is x squared, right? So we can bring this down. So knowing that u is x squared, so it means that dv du is equal to e raised power x squared, like this. But this u is still here, but so the same idea that u is x squared. So we have dy dv is equal to cos e raised power x squared, like that, because u is x squared. So overall, we can continue. So overall, we then have that dy dx. dy dx will be dy dv, this dy dv here, multiplied by dv du, dv du, multiplied finally by du dx, du dx. So it makes sense because you can see technically dv cancels dv, du cancels du. So you finally have dy dx giving you the dy dx you're looking for. So that makes a lot of sense. So having stated it that way, we can then finalize by saying dy dx now is equal to dy dv. So dy dv is cos e raised power x squared. dv du is e raised power x squared. And du dx is 2x. du dx is 2x. So that means that dy dx is equal to 2x e raised power x squared cos e raised power x squared. And that is exactly what we get. So 2x e raised power x squared cos e raised power x squared. So uh you can have multiple layers like that. So 2x e raised power x squared cos e raised power x squared. Notice that every additional layer contributes another multiplication like we just saw now. So for talking about computational graphs, deep learning represents equations as computational graphs. For example, y is equal to 3x plus 2 squared can be viewed as a sequence of simple operations. So first of all, you can multiply by 3, multiply by 3, then add 2. So you have a function, you have x, right? Multiply by 3, add 2, then square everything, square the results. So each node performs a simple computation. So you have a function x, multiply the function by 3, then to whatever you get, add 2 to it, and then whatever you get, square it. So each node performs a simple computation. During learning, derivatives flow backward through this graph. So this observation leads directly to the idea of back propagation. Now the question is, what is a gradient? I think we've talked about this a couple of times. For a single variable, dy dx is the derivative. So for functions of many variables, we have f of x of y of z. So the collection of all partial derivatives is called the gradient in that case. So for a single variable, it's just dy dx. That's the gradient. But multiple variables, the gradient of f is now the f dx, the f dy, the f dz. So the gradient points in the direction of the steepest increase of the function. So machine learning algorithms usually move in the negative gradient direction to minimize the loss because that's why we use the gradient descent method. So and that takes us to the idea of gradient descent, which we've considered a lot. Suppose the current parameter is W. After computing its gradients, you have the LDW, that's the loss function with respect to the parameter. And then the parameter is updated using new W is equal to old W minus the learning rate, eta, multiplied by the gradient, the LDW, where W is the parameter, the eta is the learning rate, the LDW is the gradient, and this update is called gradient descent. And then we talk about the gradient flow. During prediction, information moves like this. So you have an input and there are hidden layers of operations going on, and then you get an output. During learning, gradients move in the opposite direction. So you have the loss. So from the loss, you get to the output, and from the output, you have the hidden layers, and then you now work on the inputs now. So it's more like, so this during prediction, but during learning now. So you take the loss to look at the outputs. There are hidden layers, and then you now work on the input values that will give you the right kind of loss you're looking for. This backward movement of derivatives is called the gradient flow, from loss to output to hidden layers and then input. So gradient flow tells every parameter how much it contributed to the predicted error, and then so it is the parameter is then adjusted. So suppose the neural network computes x to z to a to the loss now. So here z depends on x, a depends on z, and l depends on a. So to compute the LDX now, so the rate of change of the loss with respect to x overall, we apply the chain rule repeatedly. So the LDX overall will then be the LDA multiplied by dA dz multiplied by dz dx. So like I say dA dA dz dz. So you still have your dLdx overall. So this repeated application of the chain rule is called back propagation. So imagine a neural network example. Suppose Z is Wx and A is Z squared, and L is equal to A plus 1. So you see, L depends on A depends on Z depends on X. So W here is a constant. So we wish to compute the L. Oh yeah, here we wish to compute W. So Z is a function of W here. So X is like not one of the variables to consider. So we wish to compute the LDW first. You do the LDA. So the LDA will just give us 1. Then you have to do the ADZ, which is simply 2Z. And then we do the ZDW. The ZDW gives X. So applying chain rule, we then have the LDW to be 1 times 2Z times X. And since Z is WX, Z is WX. So we then have 2WX squared for the LDW. And then if you put all of that here, so we have symbols W and X. So Z is WX, A is Z plus 2, L is A plus 1. And then if you differentiate L with respect to W, then so SymPy runs through the whole of that, and you have 2WX squared like that. Okay. And then question, why deep? So let's look at the idea of why deep connections, why deep networks rather can be difficult to train. So if you have deep networks, they are difficult to train. Suppose the neural network has 100 layers. Now you can imagine backpropagation multiplies many derivatives together. So you have DLDW equals A1, A2, A3, also up to A100. So if every derivative equals 0.5, that means you have 0.5 raised per 100. And that's just looking at it at a very simple level. So you have 0.5 raised per 100, which is approximately 7.89 times 10 raised per minus 31, which is almost zero. It's as good as zero. Now, this is called the vanishing gradient problem. If every derivative then equals, say, 2, so it means you have 2 raised per 100, which is approximately 1.27 times 10 raised per 30, like that. And then this is called the exploding gradient problem. So you have so difficulty arises because of either vanishing gradients or exploding gradients. So modern deep learning architectures use techniques such as careful initialization, normalization and residual connections, and gradient clipping to reduce this kind of problems of vanishing gradients or exploding gradients. Now, so the pattern demonstration of that, so for vanishing, right, you have 0.5 times 10 raised per 100. So that's like 7.889 times 10 raised per minus 31. That's 0.30 zeros before you get to 788 and all that. Then for the exploding one, see the number so big. So you have 2 raised per 100. That's 1.27 times 10 raised per 30, like that. So let's talk about automatic differentiation. So this is where some advancement comes in. So modern machine learning libraries such as PyTorch, TensorFlow, and JAX automatically compute derivatives. Instead of manually applying the chain rule, we simply define the computation and call the automatic differentiation engine. Internally, these libraries construct a computational graph and perform backpropagation automatically. So that's where things like PyTorch and TensorFlow come in. So here to use PyTorch, right? You import touch and W, you have touch.tensor 3.0 requires grad. That's true. So that's gradient is required. Then X is touch.tensor 2.0. So if you now say Z is WX and A is Z squared and L is A plus 1 and then L backward, you then get L grad. So here you need tensor 24 like that. So I think that is substituting 2wx squared, right? 2 w is 3. So 2 times 3 is 6. X squared. X is 2. So 2 times 3 is 6. 6 times 4, 24. That's why the answer here is actually 24. Okay. So it means that the backpropagation does not have to be as difficult as it would normally be because of libraries like PyTorch and TensorFlow. So in summary, we have this that in this lesson we learned that the chain rule computes derivatives of composite functions. Every neural network can be represented as a computational graph. Gradients measure how sensitive the loss is to each parameter, and then gradient flow moves derivatives backward through the network. Backpropagation is repeated application of the chain rule. Deep networks may experience vanishing or exploding gradients because many derivatives are multiplied together. Then modern deep learning frameworks use automatic differentiation to implement backpropagation efficiently. Although the chain rule is introduced in introductory calculus, it is the mathematical principle that enables the training of today's largest artificial intelligence models. So it's a simple concept, but it has far-reaching impact. So let's look at some practice problems, and as usual, I get to solve two of them. So I get to solve two of them. I'll solve 15 and I'll solve 15 and 17. So here you can see problems 1 to 6 clearly. You can see problems 1 to 6. I mean, these are just the basic calculus stuff. Solve the following problems without using a computer, unless explicitly stated, unless otherwise specified. Simplify your final answers. So you have questions 1 to 6 here. I mean, I did a lot of this under the calculus playlist. Then 7 to 10. Here you can see 7 to 13, in fact. You can see 7 to 13. And then, yeah, 7 to 13. Then 14, so you can say 14 downwards. So here, like I said, I'll be solving problems 15 and 17. 15 and 17. So I'll be taking care of this 15. A neural network computes Z to be 3W plus 2. A is Z cube, L is 2A. Use the chain rule to compute the LDW. So that should be straightforward. So you can also see question 16 here. So the next one I'll be solving is 17. So 17. So you can see the rest now, 17 to 20. Oh, okay. I think, can we show all of that? Yeah, we can. 17 to 20 now. Suppose the computational graph is x going to u, which is equal to x squared, implying v, cos u is L equals v squared. So use repeated application of the chain rule to compute the LDX. So, and then you have the other parts of the problems. So let's go ahead and solve problems 15 and 17, as I said, and then we bring this to a close gradually. So let's start with problem 15. Problem 15. So a neural network computes Z equals 3W plus 2. Then A is Z cube and L is equal to 2A. And then to, we need, should I say derive or whatever? Derive dl, dw. Okay, that's what we need to do. So of course, that's straightforward. So we need to compute the local derivatives. So if z is 3w plus 2, so that implies that dz, dw is equal to 3. Then next, we have a is z cube. So if a is z cube, a is z cube implies that dA, dz is equal to 3z squared. Okay. And of course, we know Z to be 3W plus 2. So we can fix that up straight up. So that's 3 into 3W plus 2 squared like that. Then lastly, we have L to be L is equal to 2A. Okay. L is 2A. So if L is equal to 2A, that implies that the L, the A, dl dA is equal to 2. Okay, and with that, we have everything we need. So overall then, overall, dl dw is equal to dl dw is equal to dl dA. So we have dl dA times dA dz, dA dz times dz dw. So dl dw then is equal to, so for dl dA we have 2, dA dz we have 3 into 3 into 3w plus 2 squared. That's okay, 3 into 3w plus 2 all squared. And the zdw is 3. So in all, we have dl dw equals 2 times 3 times 3. That's this, and this, multiplied by 3w plus 2 all squared. So that's simply 18 into 3w plus 2 squared. And that's the LDW right there. Now, on the other hand, we have okay, something really similar to that. Problem 17. So for problem 17, we have this. Suppose the computational graph, suppose the computational graph is x going to u, which is equal to x squared, and then this going to v, which is equal to cos u, and then we have this going to L, which is equal to V squared. So we need to use repeated applications of the chain rule to compute dl dx. Okay, so solution there. So let's bring out all the functions. So first of all, we have L equals, we need dl dx, right? So we start from, oh yeah, we can start from anywhere as a matter of fact, but let's start from L equals V squared. So we have L equals V squared, implying that dl dv is equal to 2v. That is settled. Then next, we have V equals cos u. So we have V equals cos u. So that implies that dv du, when you differentiate cos, you get minus sign. That's minus sine u like this. So we have that. And then lastly, we have u equals x squared. So u is equal to x squared implies that du dx is equal to 2x. So don't forget, what we need is dl dx, right? So it means we finally need everything in terms of x. So if we finally need everything in terms of x, we have to put it together like that. So, um, so I think we can tidy that up from here. Since u is x squared, so if we bring that here, since u is x squared, we have minus sine u is now x squared. We have that settled. Then we have 2v. So since 2v is cos u, so 2v, v is cos u rather. So from the fact that v is cos u, we have 2 cos u. But that's not the end. We again have that u is x squared. So from this idea that u is x squared, we still have here. So this is 2 cos x squared. Okay. So now we have this as the final outcome there, this as the final outcome there, this as the final outcome in terms of x and all that. So let me put it this way. So the final outcome, final outcome over. So you can say, so dl dx is equal to dl dv multiplied by dv du multiplied by du dx. So dl dv multiplied by the v du multiplied by the u dx. So the L dx now is equal to the L dv. The L dv is 2 cos x squared. That's 2 cos x squared times dv du. dv du is minus sine x squared, and du dx is 2x. So like that, we have the L dx is equal to 2 times 2x, that is 4x. Of course, there's a minus out here, so we have minus 4x sine x squared cos sine x squared cos x squared. But then I think we can do some trigonometric stuff still. So we have minus 4x sine x squared cos x squared. So um recall, if you from your trigonometry, recall that 2 2 2 sine 2 sine x squared cos x squared is equal to sine 2x squared, like this. So that's the reality here. So the L dx, the L dx now is equal to so if you bring 2 sine x squared cos x squared out, so you have minus 2x multiplied by 2 sine x squared cos x squared, and then the L dx is equal to minus 2x. So the whole of this now is simply sine 2x squared, like that. So the L dx finally is equal to minus 2x sine 2x squared. And that is the result for problem 17. And on that note, we are done with that. So I'll flash the problems again, and we call it a date. So here, problems, practice problems, you can see problems 1 to 8, clearly like this, problems 1 to 8. Problems 1 to 8 again. Then 9, you can see problems, you can see up to 14 now. You can see up to 14. And then 15, you can see 15, 16, clearly. 15, 16. I did 15 and 17. So you can see 15, 16, 17, right? So I did 15 and 17. And finally, you can see 18 to 20. And on this note, I thank you very much for listening. Let me know how helpful this is, and if there's something else you let me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, this is a good time to subscribe. Why not just subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives some special privileges which you'll find when you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.